Hello everyone, we are Group 11 and in this video we are demonstrating a project that is point triangulation using Graham's algorithm which is done under the course of computational geometry. Our group members are Alim Sharma with enrollment number 22113013, Kunal Bansal with enrollment number 22115083 and Shreya Jain with enrollment number 22114091. So let me begin with the problem statement. So the core problem is defined as follows. Given a set P of n distinct points in a 2D space, our goal is firstly to compute the convex hull layers iteratively so that each point is part of some convex hull, and after that we need to create a complete triangulation of the entire point set by triangulating the annular regions between these adjacent layers. Mathematically, our input is the set of points P where a point Pi has coordinates xi, yi, and our output consists of the convex hull layers L1 to Lk and a set of valid triangulation diagonals, say D1 to Dm. To further extend our project, we have implemented two real-life applications. The first one is the GIS application, that is Triangulated Irregular Network, which is used to generate terrain model of 3D structures. The second one is the stress analysis using finite element method in 2D mechanical part. Let me walk you through a three-step algorithm for convex hull layer triangulation. Let us start with step 1, computing the convex hull using Graham's scan algorithm. Our algorithm takes as input the set of n points in 2D plane and produces as output the convex hull, which is an ordered list of points forming the outermost convex boundary. So here is how it works. Firstly, we find the anchor point, that is the point with the minimum y coordinate, and if there are ties, we take the leftmost one. Next, we sort all the other points by their polar angle with respect to this anchor point. And if two points have the same angle, we keep the one that's farther from the anchor. This ensures we only include the outermost point in collinear situations. We then initialize a stack with the first two sorted points. For each remaining points in sorted order, we check the orientation using the cross product. While the stack has at least 2 points and we have a clockwise turn, we pop from the stack. And finally, we push the current point onto the stack. And the stack at the end gives us our convex hull. Now let me briefly explain the cross product, which is crucial for determining turns. The cross product of the vectors OA and OB tells us the orientation. If it is positive, we have a counterclockwise turn. If it is 0, the points are collinear. And if it is negative, we have a clockwise turn. This simple geometric test drives our entire algorithm. Now moving on to the step 2, we extend this to find multiple convex hull layers, creating a nested structure. Here is our approach. We take the convex hull points we just computed from step 1 and remove them from our point set. We then repeat Graham's algorithm on the remaining points to find the next inner layer. This process continues recursively. We keep going until every original point has been assigned to some convex hull layer. And after this step, what we get is a nested structure of convex polygons. Moving on to step 3, the triangulation, that is triangulating the regions between these convex hull layers. So firstly, for each adjacent pair of convex hulls, that is an outer and the inner hull, we first create bridge to connect them. These bridges transform a problem into triangulating a simple polygon. And then we use ear clipping method. We start by identifying all the initial ears in a polygon, and here is a triangle that is formed by 3 consecutive vertices that does not contain any other polygon vertices. While a polygon has more than 3 vertices, we choose one valid ear and we remove that vertex from the polygon, and then we add the resulting triangle to our output. We update the polygon by connecting the previous and the next vertices, and we recalculate the ear status of the 2 neighboring vertices. Finally, for the innermost convex polygon, if it has more than 3 vertices, we use fan triangulation. This means we pick one anchor vertex and connect it to all the other non-adjacent vertices, and thus efficiently dividing the polygon into triangles. So to summarize, this 3-step approach gives us complete triangulation of our entire point set while preserving the layered structure, as you can see in the output here. Let us look at the output. So firstly, we will look at algorithm visualization. So here you can enter the number of points. After entering the number of points, you can click on generate points. So here you will see that 12 random points are generated in Euclidean 2D space. After that, we will click on the compute convex hull layers. So here you will see that 3 layers are generated. So what our algorithm does is, it will first run Grahal algorithm on the total set of points and the layer L0 will be formed. After that, it will exclude the points which are included in the layer L0 and then it will further run Graham algorithm on the remaining points. And this process will go on until there are no points remaining. That is, each point is part of some convex hull layer. After that, we will click on triangulate. So here you will see these blue diagonals are doing the triangulation. So basically the region between the adjacent convex layers is being triangulated and thus the overall triangulation is being done. So let us look at another example. Let us take the number of points as 23. We will click on generate points. So here 23 random points are generated. Now we will click on compute convex hull layers. So you will see that 4 layers are generated. The first one is the yellow colored L0 layer. The second one is the L1, then L2 and then L3. Nextly, we will click on the triangulate and you will see that these blue diagonals are doing the triangulation work layer wise. So here is how a triangulation is being done using Graham's algorithm. Now let us look at our first real-world application, that is TIN. Our algorithm directly translates to creating a TIN model, which is core concept in GIS for representing a continuous 3D surfaces like terrain. Here we take each 2D point with coordinates x, y and assign it an elevation, that is z value, so that it simulates a central mountain peak. Our layer-based triangulation provides the necessary firing structure for this model. The visual output is enhanced by color coding the resulting triangulation edges based on their average elevation. So here let us run our code. So let us enter the number of points, let's say 20, and then generate terrain. So here you will see that the edges are colored in different colors. So here the green colors are the low elevation, the brown color are the medium elevation, and the white color are the higher elevation, or you can say that this area represents the mountain peak. Let us run our code for another example. Uh, for value 150, we will generate terrain. So here you will see that it represents the 3D structure of a mountain properly. This creates a realistic 3D wireframe map. Let us look at a second real world application, that is FEM stress analysis. So the layered structure defines a 2D mechanical part and a triangulation generates the necessary finite element mesh for the analysis, and the area between the hulls is solid. Here we basically simulate a stress test. Let me show you by generating the output. So let us take the value of n as 70 and run FEM simulation. So here you will see that the left side points are considered the fixed end and they are colored blue to represent the lowest stress. And the right side points are subjected to applied force and they are colored red to represent high stress. And the color gradient across the triangulation mass is based on the x coordinate, visualizing how the stress is theoretically distributed across the part. This proves the algorithm utility in generating meshes for real-world simulations. So let me show you with another example. So let us take the value as 169 and run FEM simulation. So here you will see that how the stress is distributed. It is shown by x stress gradient in the x direction. So here this is the fixed end and the lower stress end, and the red one is the higher stress end, which is in which the force is being applied.